310 is all about implicit differentiation. Feel free to stop the video or rewind as necessary. Before I begin to talk about what implicit differentiation is, I need to talk about what an implicitly defined function is. Typically, our functions are written as y equals some function of x. So for example, y equals x squared, y equals cosine of x, or something like that. Our y is typically always isolated. However, an implicitly defined function is not always written that way. Our x's and y's could be on the same side. You could have y's written within the function itself. You'll see many examples of this throughout the notes. If you have an implicitly defined function, in order to take the derivatives, you have to use implicit differentiation. I've listed the 4 steps that we're going to follow in order to take the derivative of an implicitly defined function. Please take the time to write down the steps now. Pause the video as needed. Now that you have all of the steps written, let's take a look at some of the examples. Our first example is x squared plus y squared equals 4. Notice that the x and y are on the same side. The y is not isolated, which makes it an implicitly defined function. In order to take the derivative, we're going to follow our 4 steps. Step 1 is to differentiate both sides of the equation with respect to x. That's the important part, is that it's with respect to x. So let's talk about what that means. If you have a function that's just a normal function of x, like x squared, the derivative is what we would normally think it would be, 2x. However, if you have a function that is in terms of y, when you take the derivative of x, it's technically a chain rule. We discussed this a little bit with logarithmic differentiation. So for example, if I'm taking the derivative of y squared, I have to think about this as a function y of x inside the function squared. So if I were to take the derivative of the outside using the chain rule, it's 2 times x, but evaluated at its inside, which in this case would be y of x, times the derivative of y prime of x. This explains why the derivative is 2y times y prime. However, a lot of students get hung up on why there's an extra y prime. If that's confusing, you can ignore that and just remember, if you're taking the derivative with respect to a different variable, all you have to do is take the derivative and tack on the d something. So in this case, the derivative of y squared, we instinctively want to write 2y, which it is. However, because we're taking the derivative of y with respect to x, we're going to tack on dy dx, or y prime. You're going to notice that I like to write dy dx as opposed to y prime, just because y to the first might be confused with y prime when it's in the middle of the function. So we took the derivative of the left, now we're going to take the derivative of the right. The derivative of a constant is just 0. There's step 1. Step 2 is to move all of our dy dx terms to one side. Our dy dx terms are going to be anything that has a dy dx in it, such as this 2y dy dx. That means anything that doesn't have a dy dx needs to move to the other side. So the 2x needs to subtract to the right side, and we get the equation 2y dy dx equals negative 2x. Step 3 is to factor out the dy dx. Since the left side only has one term, factoring out dy dx is just as simple as writing dy dx times 2y. And the last step 4 is to solve for dy dx. So we're just going to divide by whatever it's multiplied by, in this case, 2y. So we get dy dx is equal to negative 2x over 2y. Or if you divide the 2's out, you could simplify this into negative x over y. Notice that an implicitly defined function, its derivative can have y in it because the original function had y in it as well. Let's move on to another example. Find the tangent line for the point 1, 1 on the following curve. All right, so we need to find a tangent line. We've done this a million times. How do we find a tangent line? We need a point and a slope. First thing we're going to do is find the slope. We find the slope by finding the derivative. So I need to take the derivative of this implicitly defined function. Derivative of y to the fourth. So the derivative of y to the fourth is going to be 4y to the third. But since we're taking the derivative of y with respect to x, notice we're taking the derivative of a variable with respect to a different variable, this is where we need to tack on the extra differential. In this case, we need to tack on dy dx because we're taking the derivative of y in terms of x. This is because it's technically the derivative of the inside the y function. Again, if you don't understand y, what you need to realize is that you have to take the derivative of the term and then just tack on the dy dx if we're taking a derivative of y. For the next term, xy, this is actually a product because we can take the derivative of x and we can take the derivative of y, but because they are multiplied here, you actually have to use a product rule. So I think of the x, I think of the y as separate terms, and I proceed with the product rule. Leave one alone. Take the derivative of the second term. So the derivative of y would be 1, but we took a derivative of y, so we tack on a dy dx. Continue with the product rule, so we just left it alone, took a derivative. Now we're going to take a derivative, leave the y alone. Since I did not take the derivative of y here, it does not get a dy dx. You only add that where you're taking the derivative of y. On the right-hand side, we have x cubed, so its derivative will just be 3x squared. And since we're taking the derivative of x with respect to x, no differentials are needed. The derivative of negative x is negative 1, and the derivative of 2 drops out. So what we just did was the first step, taking the derivative of both sides with respect to x. For the next step, any term with a dy dx gets moved to the left, and any term without a dy dx gets moved to the right. So that means that I'm going to keep this term and move every other term, this one, to the right. This gives me 4y cubed dy dx plus x dy dx equals 3x squared minus 1 and minus y when we brought that y over. The next step is to factor out the dy dx. So on the left-hand side, we're going to factor out dy dx. And then finally solve for dy dx by dividing out the 4y cubed plus x. Giving us the derivative 3x squared minus 1 minus y all over 4y to the third plus x. This is our derivative, but remember, our problem was to find a tangent line. So we're going to use this derivative to evaluate it specifically at the point. Notice that we need both the x and y value in order to find the derivative value. That's why they gave us the full point. So we're going to plug in 1, 1 into our derivative function. 3 times 1 squared minus 1 all over 4 times 1 to the third plus 1. Evaluating and simplifying, we end up getting 1/5. This gives us our slope value, and our point was actually already given to us. If they only gave us one x or one y, we would plug that x in or the y into our original function to solve for the other. Now that we have our slope and we have our point 1, 1, we just simply write our tangent line, y minus 1 equals the slope times x minus 1. Our third example is just to find the derivative of the following equation. We begin by taking the derivative of the left and the right side with respect to x. For the first portion, e to the quantity x minus y, I hope you're thinking that this is a chain. The x minus y is inside of the e, making it that chain rule. The derivative of the outside, e to the x, is e to the x, but we're going to evaluate it at the inside. So we get e raised to the x minus y. Complete our chain by taking the derivative of the inside. The derivative of x is 1, and the derivative of y is also 1, but we took the derivative of y with respect to x, so we need a dy dx. On the right-hand side, the derivative of 2x squared gives me 4x, and the derivative of y squared is 2y, but yet again, we took the derivative of y in terms of x, so this is where a dy dx would be necessary. In the second step, we want to move all of our dy dx terms to the left and all of our non-dy dx terms to the right. However, if you look at the left-hand side of the equation, it's hard to tell where our dy dx term is and where our non-dy dx term is. The dy dx term is on the inside of this parenthesis. If you ever see something outside of a set of parentheses, I would suggest that you distribute it first before separating your terms. So in this case, we're going to take the e to the x minus y and distribute it into this parentheses so we can see individual terms, giving us e to the x minus y minus e to the x minus y times dy dx. And now it's a lot easier to see what has a dy dx in it and what doesn't. So this term, e to the x minus y, doesn't have a dy dx term, so we're going to move that to the right side. This one we're going to keep. This one we're going to keep on the right-hand side because it doesn't have a dy dx, and this one moves to the left since it has a dy dx terms. Moving the 2y dy dx to the other side, it makes it positive. I keep my negative e to the x minus y dy dx term. On the right-hand side, the 4x stays, and the e to the x minus y moves over to the left, making it negative. Step 3 is to factor out your dy dx term. So on the left, we get dy dx times whatever's left over after we pull it out, so 2y minus e to the x minus y. And then divide out to isolate dy dx in our final step. Gives us 4x minus e to the x minus y all over 2y minus e to the x minus y. Unfortunately, this particular derivative cannot be simplified. Even though there is an e to the x minus y in both the top and the bottom, because they're separated by subtraction, we can't cancel out one single term. This is our final answer. Let's move on to our fourth example. For problem number 4, we want to calculate the derivative at a specific point of this function. First thing I want to point out is that I made an error when I typed this up. This function is in terms of y and t, but our derivative is dy dx. Since there's no x in sight, I think I meant dy dt. So the first thing I would like to do is correct this and rewrite it as dy dt. So I just need to take the derivative and plug in the point. First step is to take the derivative with respect to t in this case of both the left and the right hand side. I noticed for this problem that I actually have a product rule, y times a cosine, and the cosine has something inside of it other than just a basic t, so that makes it a chain rule as well. Let's proceed with our derivative. Product rule. Leave it alone, take a derivative. As soon as I get to the derivative of cosine, it's a chain, so I do the derivative of the outside, negative sine, evaluated at the inside, y plus t squared, times the derivative of the inside, and when I get to the derivative of the inside, I'm taking the derivative of y with respect to t, so it's 1, but the derivative of y with respect to t is dy dt, plus the derivative of t, which is 1, plus the derivative of t squared with respect to t, 2t. I'm still not done with the product rule. That was leave it alone, take a derivative. Now I'm going to add, take a derivative, 1 times dy dt, leave it alone. That was the derivative of the left side. The derivative of the right side is thankfully much easier, just 3t squared. At this point, you can take the dy dt's and isolate them. What you would actually need to do is take the negative y sine of y plus t squared and distribute it to each of these individualized terms inside the parentheses before you can actually separate your full dy dx terms, your dy dt terms and your non-dy dt terms. However, because this problem is not actually asking us for the derivative dy dt and just to evaluate it, you can also use a shorthand method for implicitly defined functions. Once you've taken the derivative, since this statement is true, you can just start to plug in 0 and 5 pi over 2 and just solve for dy dt for that specific point. So let's go ahead and just start plugging in our values. Plug in 5 pi over 2 for y, 5 pi over 2 for y again, 0 for t again, times dy dt, which I don't know. That becomes my variable in this case. Plugging in 0 for t. Again, dy dt we don't know. That's what we're looking for. Y is 5 pi over 2 plus 0 squared equal to 3 times 0 squared. As I start to simplify here, I can start to evaluate this first term. Sine of 5 pi over 2 is the same thing as sine of pi over 2, which gives me a value of 1. So this whole expression right here is 1 times negative 1 times 5 pi over 2 gives me negative 5 pi over 2. In my next set of parentheses, I have 2 times 0, which is 0, plus 1 plus dy dt is just going to leave me dy dt plus 1. My next term, dy dt times cosine, I have cosine of 5 pi over 2, which is the same thing again as pi over 2. So cosine of pi over 2 is going to give me 0, so I have dy dt times 0. And then on the right-hand side, simplifying gives me 0 as well. Because dy dt times 0 is always going to be 0, I can just cancel out that second term, leaving me with negative 5 pi over 2 times dy dt plus 1. To continue to solve for dy dt, since that's what I'm after, the derivative value at this specific point, I'm going to multiply by 2 over negative 5 pi, or divide by negative 5 pi over 2, whatever way you want to think of it. If I do that, I get dy dt plus 1 equals 0, because if I divide 0 by negative 5 pi over 2, I still get 0. Solving for dy dt, all I have to do is subtract 1, and that gives me my derivative value that I was seeking. We have one more problem. Find the second derivative for x squared plus y squared equals 1. So how do we take the second derivative for an implicitly defined function? Well, it's similar to the way we've done it before. If we want the second derivative, we find the first derivative and then find the second derivative. So the first thing we have to do is find the first derivative. You may feel like this is a deja vu, and this is because we did this example in example 1. So from example 1, I could tell you that dy dx is equal to negative x over y. If we hadn't had this problem before, we would go through the entire four-step process as we typically would do for any implicitly defined function. Now we're going to take the derivative again. The derivative of dy dx, the derivative of the first derivative, is the second derivative. So we're going to get d squared y over dx squared. The derivative of the right-hand side is a quotient, so we follow the quotient rule. Low d high minus high d low, and the derivative of y is 1, but we took the derivative and it's dy dx. You may be wondering why it's dy dx and not d squared y dx squared, and that's because I'm taking just the derivative of y. When you take the derivative of y prime, that's what yields you y double prime. The derivative of just a plain old y will always yield dy dx, just a singular first derivative. Finishing the quotient rule, all over, low, low. If we simplify, we get that the second derivative is equal to negative y plus x dy dx all over y squared. Unfortunately, our second derivative cannot have the first derivative in it. So if you need to write the second derivative, you need to replace dy dx. And what does dy dx get replaced by? Well, with whatever dy dx is. In this case, dy dx was negative x over y, so I'm just simply going to replace dy dx with negative x over y. If you just need to find the second derivative, once you've replaced dy dx, you're done. However, most of the time, if this is multiple choice, your answer is not going to be written like this. In order to get rid of a fraction within a fraction, you can multiply throughout by that denominator. So in this case, I can get rid of the division by y in the second term by multiplying y throughout on top and bottom. Distributing y on top, negative y times y gives me negative y squared. For this second term, x times negative x over y, the y's cancel when you multiply, and x times negative x gives me negative x squared. All over, on the bottom, y squared times y to the third. And this gives us our final second derivative. And this concludes our notes. We'll talk more about implicitly defined functions after our quiz on Tuesday.